Welcome to the class of optical communication, and today we will discuss about the meridional ray and the skew ray. These two type of ray which is transmitted inside the optical fiber cable, and we will discuss about the acceptance angle for the meridional ray and the acceptance angle for the skew rays. My name is Himanshu Nagpal, assistant professor in EC department of AKGEC Ghaziabad. So first of all, we will talk about the what are the meridional rays and what are the skew rays. First of all, we'll see the light is propagated inside the optical fiber can be propagated with two mechanism. First of all is one is known as the meridional ray and another one is the skew ray. Means if I say this is the optical fiber cable and this one is the core. If light is traveling inside the optical fiber cable, if this type of transmission, and say this is a axis of the fiber core, if the ray crosses the axis of the fiber of the core and the ray after reflection, the ray will maintain its orientation, or you can say maintain its plane after reflection. Means in plane of incident ray and the plane of reflected ray both are same, then that type of ray is known as the meridional rays. And another type of ray, that is skew rays. If the ray enters the optical fiber cable and it will transmit along the optical fiber cable, along the boundary of the optical fiber after each reflection. Let's say if I say this is optical fiber cable and let's say this one is the hollow inside. If the light is transmitted inside the optical fiber cable like this one, and the after each reflection the plane of light will remain same, then that type of ray is known as the meridional rays. And this type of ray is always crosses the center of the fiber core, means axis of the fiber core, always crosses the axis of the fiber core. Now another type of ray, that is a skew ray. This skew ray enters the optical fiber and it will travel along the boundary of the optical fiber cable, means along the boundary of the core, and after each reflection it will travel to the another part of the optical fiber core at another plane. Means the incident plane plane of incident ray and the plane of reflected ray will be different, and you can say the ray will follow the helical path along the boundary of the core cladding interface. That type of rays are known as the skew rays. Now see, a light ray is launched in a plane containing the axis of the fiber, and this light ray after total internal reflection travels in the same plane. That type of ray is known as the meridional rays. So in this situation the ray will always cross the axis of the fiber, and these are known as the meridional rays. Let's say this one is the core and this one is the cladding. Here if I say this ray enters the optical fiber cable at this point A, and this theta 1 is the angle which makes the input ray with the forward axis, makes an angle of theta 1. When it enters the optical fiber ray, it reflected at point B. The incident ray, and the plane of this reflected ray will remain same, and this ray will always crosses the fiber axis of the core. Clear? So this type of rays are known as the meridional ray. So first of all, we'll discuss about the numerical aperture for the meridional rays. Now let's say this is make an angle of theta 1 and this is makes an angle of theta 2, and this incident angle is phi and this reflected angle is phi. Clear? So, and if I say this is point A, this is B, and this is point C. Now see this one. Let's say this one, light ray incident on the fiber core at an angle of theta 1, which I already told you, which is less than the acceptance angle for the fiber, and acceptance angle is the maximum angle below which the ray, if the ray enters into the optical fiber, will perform the total internal reflection, and above which if theta 1 is greater than the acceptance angle, then that type of ray or that type of meridional ray will not perform the total internal reflection, and therefore it will not be propagated inside the optical fiber cable. Now let's say if the incident angle at the air core interface, it makes an angle of theta 1 and which is less than the acceptance angle for the theta A, and the ray enters the fiber from a medium air into the core, which is having a refractive index n1, which is slightly also greater than the what, n2. Now apply the Snell's law at this point. Snell's law at point A. You will see that when you apply the Snell's law, at point A, you will see that n naught multiply में sin theta 1 is equal to n1 into में sin theta 2. From this point you will see that n naught multiply में sin theta 1 is equal to n1. n1 is the refractive index of core, n naught multiply में theta 2. This is a Snell's law. Now Snell's law at this point. Now see, I want to calculate the relation between the theta A, n1, n2 and numerical aperture. I want to see some relationship between the numerical aperture, the acceptance angle and the n1, n2. Clear? So I have to eliminate this theta 2. So to eliminate this theta 2, here you will see from triangle ABC, you will see here that phi is equal to pi by 2 minus में theta 2. So phi is equal to pi by 2 minus theta 2, therefore theta 2 can be written as pi by 2 minus में phi. Just put the value of theta 2 in this equation, you will get n naught into में sin theta 1 is equal to n1 sin pi by 2 minus में phi, and this will equal to n1 into में cos phi. So n naught into में sin theta 1 equal to n1 into में cos phi, and this cos phi can also be written as 1 minus में sin square phi की power में 1 by 2. This is n naught sin theta 1. Clear? Now for the limiting case, if I say the ray which is enter at optical fiber core at point A, if this makes an angle of theta 1 is equal to maximum acceptance angle, then this ray here, this phi will become what? This phi will become equal to critical angle. Clear? For the limiting case at the entry point, and there will be a limiting case at the intersection point at point P, then theta becomes theta A and phi becomes phi c. So you will see here that sin theta a, this is n naught into my sin theta a, n naught into my sin theta a will be equal to what? n1 1 minus में sin square phi c, sin square phi c की पावर में 1/2, की पावर में 1/2. Clear? Now see this phi c, as we know that sin phi c is equal to what? n1 by, sorry, n2 by n1. Just put this value of sin phi c here. You will see that n naught is equal to what? N naught is what? Refractive index of air, and this n naught is equal to 1. So just put this here, value here. Sin theta a will become equal to what? n1 1 minus में n2 का स्क्वायर अपॉन में n1 का स्क्वायर की पावर में 1/2. On taking the LCM and LCM this one, and n1 will be get cut out, you will see here that sin theta a will become equal to n1 का स्क्वायर माइनस में n2 का स्क्वायर की पावर में 1/2, and this is sin theta a. So acceptance angle will be what? Acceptance angle will be equal to n1 square माइनस में n2 का स्क्वायर की पावर में 1/2, सॉरी, साइन इनवर्स ऑफ theta a will equal to sin inverse of this term. And you can also say sin theta a is equal to the numerical aperture of the optical fiber cable for the meridional rays. We always prefer to have a transmission through a meridional rays, because meridional rays will take little time or will take less time as compared to the skew rays for getting a for the same distance transmission. Means for the same distance transmission, skew rays will take a more time as compared to the meridional rays, and the meridional rays will always utilize the full area with the full area of the optical fiber core with full efficiency. Clear? And for the meridional rays, the light attenuation is less as compared to the, if the skew ray is transmitting the signal at the transmitter side, and in that type of ray the attenuation is the maximum, because it will cover a more distance as compared to the meridional rays. Skew ray travel the more distance. When it travels the more distance, and the more reflections will take place along the boundary of the optical fiber cable. When there are more reflections along the boundary of the optical fiber cable, means there will absorption, scattering, attenuation will also be more as compared to the meridional ray transmission. Clear? So we always prefer to have a transmission through a meridional ray, and this one is a numerical aperture for the meridional ray. And what is this? And so this is theta a, as I have told you. Now there is another term, that is a relative refractive index difference. This delta is equal to n1 square माइनस में n2 square upon में twice of n1 का whole square. Now this relative refractive index can also be expressed in terms of numerical aperture. This delta is equal to, and as I've known, you know that sin theta a is equal to numerical aperture, and this is equal to n1 square minus में n2 का square की power में 1/2. So we'll see here that na का square numerical aperture का whole square will be equal to what? n1 square minus में n2 square. Just put this value here, numerical aperture here, and this is equal to, so this is relative refractive index can also be written as numerical aperture का whole square divided by twice of n1 का whole square. So numerical aperture can also be defined in terms of the relative refractive index, that is n1 multiply by 2 delta ki power 1 by 2. Clear? So we will see that the numerical aperture optical fiber cable depends on the refractive index of the core, relative refractive index of the core and cladding. Clear? So if the delta is very less than 1, then delta can also be written as n1 minus n2 divided by n1 if delta is very less than 1. So in terms of numerical aperture can be defined as the, because as we know that numerical aperture is what, sin theta a is equal to numerical aperture, and this numerical aperture defines the ability of the optical system to collect all the light incident on it in one area. It is the ability of the fiber, optical fiber, to collect most of the light energy. If I say this is a core and this one is theta, this is acceptance cone, so most of the light which is enters within acceptance cone will be propagated inside the optical fiber cable and will also perform the total internal reflection. So it is the ability of the optical fiber cable to collect all the light enter into the optical fiber and perform the TIR. So this numerical aperture, ultimately we can say this numerical aperture will depend upon what, acceptance cone or acceptance angle. So it is the ability or light collecting efficiency of the fiber, that, and also it is the measure of the amount of the light ray can be accepted by the fiber. Clear? So numerical aperture is the ability of the optical fiber to collect most of the light enter into the optical fiber and will perform the TIR, and so therefore this numerical aperture depends on the acceptance angle. Now as we know that sin theta a is equal to numerical aperture, so you can see that the smaller the value of Na, smaller will be the value of acceptance angle, and the smaller is the power accepted by the fiber. Now next one is the skew ray. If the ray is launched in a plane containing the axis of the fiber is not launched, अगर कोई ray launch हो रही है optical fiber में and if will not launched in a plane containing the axis of the fiber, then that type of ray is known as the skew rays. For example, if the ray is launched at some angle such that it does not intersect the axis of the fiber, then after total internal reflection it will go to some other plane. Let's say if I say this is a optical fiber cable, and if the ray enters into the optical fiber cable and it will not the core fiber axis, if it will not to cross the fiber axis core, then it will enter into the another plane and will be known as the skew rays. So the ray essentially will spiral around the axis of the fiber cable and the rays are called as a skew rays. Let's see, I can show you here. Now see, this is a core and this one is the cladding. If the ray enters into the optical fiber at some angle such that it will not crosses the optical fiber cable, crosses the core axis, this one is core axis, it will move around the core axis like this one, but it will not cross the core axis, and after each reflection it enters into the another plane. So that type of rays are known as the skew rays. If I take the cross sectional view of this optical fiber cable like this one, so the ray will enter like this one and will travel like this further this down the optical fiber cable, and after each reflection the angle which it makes, that is equal to 2 gamma, and the gamma is the angle which it makes with the core axis, means this one is the radius of the fiber, radius of the fiber core. Clear? Now, now see, this one is the ray path within a fiber core for a skew ray incident at an angle theta s. If I say this is a skew ray and this skew ray enters the optical fiber cable at this point, at point A, and it will make a angle theta s. Clear? And this ray will coincide at point B, and after reflection it will move this one. Clear? So the angle which it makes, like this one, this is a at this point we take planars, the angle after each reflection it will make angle of what, phi, and with the radius of the core it makes an angle of gamma. When we see this projection like this one, so this one is known as the gamma. Clear? Now see this one. A skew ray is incident on a fiber core at point A at angle theta s to the normal at the fiber end face. The ray between A and B, it is necessary that to resolve the direction of ray path AB to the core, and the incident and the reflected ray at point B are in the same plane. That is known as the simply cos phi. If the two perpendicular planes of path AB are transverses considered, then the gamma is the angle made between the core axis and the projection. Means gamma is the angle made between the projection and the radius of the core. This one is the radius and this one is the projection of this one here. Clear? And theta is the angle between the ray and the line AT. So you will see that the reflection at point B will be equal to what? Can be given as cos gamma multiply by sin theta is equal to cos phi. Now I want to calculate the numerical aperture or acceptance angle for the skew ray. You will see here that this theta is what? This theta is what? This is here. Clear? This is theta. This is theta. And this theta can be related to the acceptance angle for the skew ray, because how can we relate this theta with theta s? This theta and this theta s can be related by the using the Snell's law at point A. If I uses the Snell's law at point A, means A is what? A is the interface between the core and the air. Means if I say this is a fiber core, this A, the ray enters into the optical fiber at point A. So this is the interface between the core and the fiber. So using a Snell's law at this, n naught into my sin theta s will be equal to what? N1 into my sin theta. Clear? And cos phi is the this angle of incident angle and the reflected angle. So we will see here that the cos gamma into my sin theta equal to cos phi, and this cos phi can also be written as, this is cos gamma sin theta is equal to cos phi, and this cos phi can also be written as 1 minus में sin square phi की पावर में 1/2. This is sin square. Clear? Now see, you will see here that on applying the Snell's law at this point, so you will see that sin theta s is equal to n1 into my sin theta, or you can also say that sin theta is equal to sin theta s divided by n1. Clear? Now see, if I say this is phi, now if I say this theta s is the limiting case for the acceptance angle of the skew ray, then this theta s will become equal to what? Acceptance angle for the skew ray. This theta s will become equal to the what? Acceptance angle for skew ray. Clear? And this phi will become what? This phi will become the critical angle. So this phi can also be written as phi c. So for the limiting case, you will see here that phi become equal to phi c and theta a, theta s. This theta s will become equal to theta as, acceptance angle for the skew ray. Now, so just put this here, cos gamma into my sin theta, cos gamma into my sin theta equal to cos phi c. As it is a limiting case, so you will see that this is angle cos phi equal to 1 minus में n2 का square, you will see here also you can write it as 1 minus में sin square phi c की power में 1 by 2, and this one is equal to sin phi c is equal to what? As we know that critical angle is equal to what? Sin phi c is equal to n1 by n2 by n1. Clear? So you will see here n2 by n1 की power में 1 by 2. Clear? On just putting this value. Now I have already told you this is Snell's law at this point. So then theta a sin theta will become equal to what? This sin theta will be equal to what? Sin theta a upon में n1. Equal to theta as. So you will see here that sin theta can be written as sin theta as divided by n1, as we know that n naught is equal to refractive index of air is equal to 1. So just put this value here, sin theta. So we'll see here cos gamma is multiply में sin theta की, just put the value of sin theta here, sin theta as upon में n1 is equal to n1 का स्क्वायर माइनस में n2 का स्क्वायर की पावर में 1 by 2 अपॉन में n1. So we'll see here the n1 becomes cancel out and this cos gamma sin theta as will become equal to n1 square minus में n2 का स्क्वायर की होल पावर में 1 by 2. Clear? And this is what? Sin theta as, cos gamma into sin theta as can be equal to what? Numerical aperture of the optical fiber. As we know that this numerical aperture is what? This numerical aperture is of the optical fiber cable, not for the skew ray. Clear? But acceptance angle for the skew ray can be different as compared to the for the skew ray is different as compared to the acceptance angle for the what? For the meridional rays. Clear? So cos gamma into sin theta as is equal to numerical aperture, and from the above equation you can say that acceptance angle for the skew ray is larger as compared to the acceptance angle for the meridional rays, and addition of skew rays increases the amount of light capacity of a fiber. So in large numerical aperture the increase may be significant. Skew rays tend to propagate near the edge of the fiber core, and this addition of skew ray increases the amount of loss in the fiber. I have already told you it travels a further distance as compared to the meridional ray, so amount of loss will be more as for the skew ray. So this skew ray tend to propagate near the edge of the fiber and a large portion of the number of skew rays that are trapped in a fiber are considered to be as a leaky ray. When it travels along the boundary, a large portion of the number of skew rays trapped in the fiber core are considered to be as leaky. Means this type of rays, the information containing this type of rays can be leaked out from the from the core and cladding interface. So at that point, the thickness of the cladding is most important, so that the security or information cannot be leaked out. So leaky rays are predicted to be total internal reflected at the boundary, and these rays are partially reflected because of the curved nature of the fiber core. So this one is the whole, we have told that this one is the whole ray theory transmission for the optical fiber cable, and the limitation of the ray model theory, that it gives an impression that during the total internal reflection the energy is confined to the core only, and in reality this optical energy is spread in cladding also. So in the ray theory transmission we have not expressed the, or we cannot find out the how much the energy can also be spreading out in the cladding. So this is the limitation, and this ray model theory does not speak of the discrete field patterns for propagation inside the optical fiber core, and this ray theory can also not be explained when the core size becomes comparable to the wavelength. So this so for the single mode fiber, the radius is very less, the radius of the core is very less, so this ray model theory cannot be justified for the single mode fibers. Thank you. The book I have referred for preparing the slides, that is Optical Fiber Communications Principle Practice by John M. Senior. Thank you.